Welcome SYBsc Physics student, semester 4, paper first, Oscillation, Waves and Sound, chapter 2nd, Damped Oscillations, and today's topic is average energy of the damped oscillation. Average energy of the damped harmonic oscillations. So here for the average energy damped harmonic oscillations, in a damped harmonic oscillation we have seen that the amplitude decreases with the time, and which means that the energy associated with the system does not remain constant, and the damping force acts as an agent in the process of dissipation energy, and the rate of the dissipation of energy is nothing but the rate of the doing work against its damping force. So therefore here the damping force Rx is equal to R dx by dt, R dx by dt, and here this is equation 1. And the rate of doing work against the damping force, the rate of doing work against the damping force is R dx by dt is equal to into dx by dt is equal to R v square, or it is written as R dx by dt bracket square. This is the equation number 2. So from the law of the conservation of energy, this must be equal to the loss of energy of the system. And now the equation for damped harmonic motion is m d square x by dt square plus r dx by dt plus kx, and that is equal to 0. This equation number is 3. Equation number 3. And multiplying each term by dx by dt. Multiplying each term by dx by dt. So here this equation 3 becomes m d square x by dt square into dx by dt plus r dx by dt bracket square plus kx dx by dt, that is equal to 0. And this equation is the equation number 4. equation number 4. So therefore here we write 1/2 m d of dt dx by dt bracket square plus r dx upon dt bracket square plus 1/2 k into d of dt x square, that is equal to 0, and this equation is a 5. So the first term in our equation represents as the kinetic energy with the time, and this second term is represent the rate of doing work against the damping force, and the last term is represent the rate of change of the potential energy. So here this is the kinetic energy, then this is the work done against or the damping force. It is the damping force, and the last term it is the rate of change of the potential energy with the time. And if we denote the kinetic energy by Ek and the potential energy by Ep and dx by dt by V, then this equation 5 becomes. So therefore here we write d dt of Ek plus d dt of Ep is equal to minus Rv square, is equal to minus Rv square. This is the equation number 6. And here this equation states that the rate of change of mechanical energy is equal to the rate of doing work against the damping force, and it is called as the energy equation. This is the energy equation with the damping. Energy equation with damping. Energy equation with the damping. Okay, and so therefore if the it is clear that the damping force is a 0, so therefore this equation written as d dt of Ek plus d dt of Ep, and that is equal to 0. So therefore here Ek plus Ep, and that is equal to constant, and that is equal to E. Constant Ek plus Ep, that is equal to constant, and that is the E. Or in actual practice, at any instant, the displacement of this damped oscillator is Ek plus Ep. So here this x is equal to, x is equal to a e raised to minus rt upon twice m into sin pt plus alpha. Sin pt plus alpha. So I again write this equation here. These are the displacement of the damped oscillator, that is x is equal to A e raised to minus RT upon twice m into sine pt plus alpha, sine pt plus alpha. And here this equation is a 6, and this here we know this equation is a 7, this equation is a 8. Okay, so therefore here this equation is a 9. Equation is a 9. X is equal to a raised to minus RT upon twice m sine pt plus alpha. Okay, and so therefore here this ek is equal to 1/2 m dx by dt bracket square. This is equation number 10. And here we know this EP is equal to 1/2 k x square. This is the equation number 11. Okay, so here these ek plus ep, and here this ep is equal to 1/2 m omega square a square e raised to minus RT upon m sine square pt plus alpha. This is the equation number 12. And so therefore we got the total energy is equal to kinetic energy plus potential energy, and that is equal to ek plus ep. This is the equation 13. This is the equation 13. So during the damped harmonic motion, the energy of the oscillation does not contain but does on decreasing continuously, and therefore it can be, that is consider the average value of an oscillator over the complete period of the oscillation, and it can be found by considering the average value of the terms on the RHS of the equation. These are 13. Okay, so therefore average value sine square pt plus alpha is equal to integration 0 to t sine square pt plus alpha into dt, this divided by integration 0 to t into the dt, sin square pt plus alpha dt 0 to t into the dt. And here this is the equation 14. This is the equation 14. So therefore here by solving this sin square pt plus alpha, that is average value, and this is the average value. So sin square pt plus alpha, average value of this, that is equal to 1/2. That is equal to 1/2. So similarly average value of the cos square pt plus alpha, that is equal to 1/2. And so therefore the average value of sin square sin pt plus alpha into cos pt plus alpha, and that is equal to the 0. That is equal to 0. So therefore average energy over a period E vector, so therefore average energy over a period is equal to E vector So that is equal to E vector is equal to 1/2 m a square e raised to minus RT upon m into r square upon 8m square plus p square upon 2 plus omega square upon 2. So this is the equation number 60. Equation number 60. Okay, and for the low damping, these r square upon 8m square is can be neglected in comparison with the omega square. Okay, and so therefore also in such case, that is p equal to the omega. So E bar is equal to 1/2 m a square e raised to minus RT upon m into the omega square. And so therefore this E bar is equal to 1/2 m omega square a square e raised to minus RT upon m and so therefore this E bar is equal to E0 e raised to minus RT upon the m. This is the equation 17. E bar is equal to E0 e raised to minus RT upon the m, and that is the average energy of the damped oscillator. Average energy of the damped oscillator. This equation 17, E bar is equal to E0 e raised to minus RT upon the m. This is the average energy of an oscillator, decreases exponentially. So therefore these equation 17 is average energy of damped oscillator. Decreases exponentially. Average energy of the damped oscillator decreases exponentially. And when we draw this graph of this, zero and here such type, that is this is E0 e raised to minus RT upon m. So this is the T versus the E0. This is the E bar. So here this figure 1 shows the E0 E bar e raised to. So this is the graph, and energy of the damped harmonic oscillator. Energy of the damped harmonic oscillator. Okay, so this is the average energy of a damped harmonic oscillator. Okay, so this topic is completed here, and in the next video lecture we will see the quality factor and application of the LCR series circuit. Okay, so thank you all of you.